This is the final part of this week's lectures. What we've seen in the first 4 parts, as I've already said, T cell activation, specifically CD4s, the role of cytokines in shaping that CD4 response, the importance of understanding the interaction between different cytokines and how that in turn can shape both the adaptive and innate immune response. And in our last short lecture, we saw that a naive T cell is a type of stem cell. It is open, it is uncommitted, and as soon as it sees a specific cytokine, it will be driven down a particular lineage. This commitment, this differentiation, is associated with waves of gene expression. Either expression, turning on, in the case of IL-12, Th1, interferon gamma, Th1, or IL-4, Th2, and this differentiation is associated with the expression of specific transcription factors, and that there is reciprocal inhibition of Th1 and Th2, for example. These are all very tightly regulated processes. They ensure that we have a balance of all of these T helper subsets. They are produced when needed, in numbers that are needed, and our T regulatory T cells shut them down as soon as the threat has passed. So what about inflammatory diseases? What happens there? What do we see in terms of cytokines and CD4 positive T cell subsets? This is a cross-section of skin. Again, it's a fairly complicated diagram, so let's first of all check what we're looking at. We start at the top with the outermost layer of the skin, our stratum corneum. This is what faces the outside. We're looking at 3 different phases in this diagram. We're looking at what's called non-lesional, which is healthy skin. We're looking at acute inflammation, and finally chronic inflammation. And this is a picture of atopic eczema or dermatitis. So what happens then? In healthy skin, we may see an initiating event which is antigen. In this healthy skin, we see a mixed T helper cell population. Importantly, the size of these little cells here reflects the numbers. So small size, meaning relatively few T helper cells in unaffected skin. And you can see we have some Th17, Th1, Th2, and T helper 22. In the acute phase, we start to see allergens and physical damage to our epidermal barrier. This is through itching, scratching, possibly infection. And now we see our first changes in our T helper subsets. We now start to see the predominance of our T helper 22 and T helper 2 subsets. We're seeing lots of interleukin 4 and so on. We're starting to produce antibodies which will be used to fight the infection, to turn on our innate immune cells. We're seeing recruitment from the circulating immune cell compartment in our blood. So now we're seeing a huge influx of innate and adaptive immune cells. As we see more T helper 22, T helper 17, T helper 2, we start to see increases in cytokines such as interleukin 17 and interleukin 22 and interleukin 4, all of which is now driving a particular phenotype that we associate with an allergic disease. In the final chronic stage, what we're seeing now is more extreme tissue remodeling. We're seeing lots of thickening here of our epidermal, our underlying dermal layer. And now we can see very strong numbers of T helper 2 cells as well as T helper 22. We're also starting to see an increase in T helper 1 and 17 as well. So we're starting to see lots of immune cells, but which tend to be predominated by T helper 2 or T helper 22 cells. These are driving a particular phenotype that we see with the thickening of the epidermis and this cyclic repair and fighting of infection. So how does this come about? What is the dysregulation of these subsets? Why doesn't this happen in everyone? Why do we only see a few people who are faced with this type of chronic inflammation? One reason is, and this is an idea that's been around for quite some time now, is called the hygiene hypothesis. What I'm presenting here is a fairly simplified version of this, but really it was put forward to explain the excessive T helper 2 cell activation that we see in people with allergic diseases. So first of all, we begin with a genetic predisposition. Now this is now absolutely clear. There's been lots of genetic studies that have been done, and it is absolutely clear that allergy has a genetic basis. This genetic basis can lead to a more fragile epidermal barrier, leading to greater allergic sensitization. It can also lead to an overstimulation of our immune system. So what the hygiene hypothesis says is that in our modern society, where we tend to avoid germs, smaller families, use of antibiotics, that this does not allow our immune system to see germs. In effect, we are too clean and too healthy. As a result, we start to see a very powerful T helper 2 response, which drives the production of asthma and allergy. However, on the other hand, a protective response is seen through early childhood infections, older siblings, daycare exposure, living on farms. In other words, precisely those environments where you would be more likely to come into contact with infectious agents. And there's good evidence that children in that environment have a lower risk of developing asthma. So what we're seeing is that we have evidence for who we are, our genetics, in combination with the environment, which is starting to shape the way our immune system is. And that this shaping of our immune system is occurring, at least in the example we're looking at here, very, very early in our lives. Let's look at that in a little bit more detail. Neonatal immunity is characterized by a strong T helper 2 response. So our default position when we are born is that we have a very strong T helper 2 response. This T helper 2 response will predominate in the absence of infections. In the absence of infections, we will see a weaker T helper 1 response, and this will drive a very strong T helper 2 phenotype. Think back to how we saw that reciprocal antagonism between T helper 1 and T helper 2, that cross-regulation. You remember that we said that T helper 2 inhibited T helper 1 and T helper 1 inhibited T helper 2. So now you can imagine that if we have the predominance of one particular T helper subset, in this case T helper 2, that will have a lesser, there will be less effect from T helper 1s suppressing or controlling that T helper 2 phenotype. So let's have a look what this diagram is showing us. What we can see here is our Th1 and our Th2 responses. We now understand that our T helper 1 response is driven by intracellular pathogens such as viruses, whereas our T helper 2 response is driven by extracellular. Whereas our T helper 2 response is driven by extracellular infections such as parasites. We can see that, as we've already talked about, T helper 1 is associated with specific cytokines such as interferon gamma, whereas T helper 2, a different set of cytokines including interleukin 4. T regulatory T cells, in the presence of IL-10 and TGF-beta, of course, they can inhibit both cell-mediated immunity as well as our Th2 immunity. Now, in the absence of any of these infections or an imbalance of, for example, even our gut biota here, which is our commensal bacteria, and the role of our commensal bacteria in our gut and also our skin is receiving increasing attention in terms of our immune health, what we start to see is we start to see a skewing of subsets. That in the absence of some infections early in childhood, the increased use of antibiotics, the absence of certain infections, for example, that we start to see things start to shift. That we've lost all of those checks and balances that we previously might have had, and that can lead to a skewing of our immune cell subset in genetically predisposed individuals. What we see here is our skin, and our skin, of course, as I've talked about, it contains tissue-resident immune cells. And we're looking at one of these to start with called a Langerhans cell, which is really an immune sentinel cell in the skin that expresses both MHC1 and MHC2, and it can present antigens to T cells. In other words, it's a type of dendritic cell. They can contact skin-resident memory T cells as well as travel to the lymph nodes to activate naive and memory T cells. So this is our skin-resident antigen-presenting cell. It's lying in wait in our skin. If an infection comes, it can talk immediately to T cells, which are also tissue-resident, our memory effector cells, leading to an expansion of that subset. It can also travel back to the lymph node to recruit further T cells if needed. So what we see is that in normal, healthy human skin, we have very low levels of antigen. We have our Langerhans cell, and we have a balance between our T regulatory T cells, which of course is tolerance. Tolerance is the absence of an immune reaction. And we have our T effector memory cells, which of course are effector cells in immunity. So in a healthy condition, those two, if you like, competing activities balance each other out. We have homeostasis. Now, as soon as we have infection, of course, this balance changes. In the presence of an infection, a pathogen, we start to see the T effector memory response predominate. For example, if we have chronic inflammation, as we've already talked about, we can start to see an overproduction of interleukin 17 and interleukin 22 at the cost of our T regulatory T cells. We see a disruption of homeostasis. We now see the steady state now shifting to immunity rather than tolerance. And of course, in the absence of any corrective mechanism to bring that imbalance back in line, we now start to see our pathological changes, leading from this healthy skin with a well-defined and healthy-looking epidermis to a much thickened epidermis here and a breaking up of this external barrier of our skin. These are pathological changes that are associated with long-term imbalance in our T helper subsets and long-term imbalance in the cytokines produced by these T cells. The reasons for this are certainly environmental. They are also genetic, and it is the complex interaction between genetics and environment that can lead to these chronic diseases. There is still a great deal of investigation going on to really understand susceptibility and the reasons for why some people develop these chronic diseases and not others. So in summary then, the cytokine environment determines the profile of T cell activation. We've seen that in chronic inflammation, the cytokine environment tends to be dominated by one or just a few cytokines, which really drives a skewed production of T helper cells such as Th17 or T helper 2. The cytokine environment also has a very big effect on our non-immune cells such as epithelial cells, as well as immune cells in our innate and adaptive immune systems. We've talked about how specific cytokines drive the production of different CD4 positive T cell subsets: interferon gamma, Th1, interleukin 4, Th2, interleukin 6 plus TGF beta, Th17, TGF beta, IL-10, T regulatory T cells. So you can already see that an imbalance in cytokines leads to an imbalance in these CD4 positive T cell subsets. T regulatory T cells are important for immune tolerance and immune suppression, and they regulate T cell activity through cell-cell contact, as well as the activity of the cytokine interleukin 10. In addition to the regulatory effects of T regulatory cells, we also see there is counter-regulation between our different T helper cells. For example, Th1 and Th2 oppose and balance each other out. In the absence of a potent Th1 response, we will start to see a potent Th2 response, for example. And of course, that's associated with an allergic reaction. Ongoing cytokine imbalance will lead to tissue remodeling, thickening of our epithelial layer, narrowing of airways, etc. And that this is, of course, driven by this imbalance in our T helper subsets.